Join me here on the shores of the mighty Avon, where the topic of our talk is a million miles away. Perhaps surprisingly, the same tidal forces responsible for the rise and fall of the water level here cause some of the most violent, dramatic events in the solar system.
Thank you, Professor Cox. That's right, today we're going to learn about the comet Shoemaker-Levy 9, which was captured by Jupiter's immense gravitational field, ripped apart by tidal forces, and then plummeted into Jupiter's surface at approximately 134,000 miles per hour. First of all, we're going to hear from Mei a bit about the mechanics of comets and their orbits, and then Becca and Sophie are going to tell us a little bit more about SL9 in detail.
Let's talk about classical mechanics, as it deals with how objects move under the influence of forces. You could say it's the study of, why does that move when I kick it? Welcome to the three-body problem, a cosmic conundrum where things get messy really quickly. The catch? There's no analytical solution to this problem, and that's where numerical solutions come into play. Envision analytical solutions as a crystal ball that discloses the entire trajectory of a system, while numerical solutions are like a game of connect the dots, linking the points together to reveal the bigger picture.
The comet Shoemaker-Levy 9 was a comet that was of huge impact in the 1990s. It was discovered by Jean and Carolyn Shoemaker and David Levy in 1993. For thousands of years, comets have inspired fear and dread throughout many cultures and have been known to be called menace of the universe. The ancient Greeks and Romans knew them as omens of doom and that they would bring great tragedy if one was seen.
Supernovae are some of the most violent, explosive events in the universe. They're also the catalyst for the formation of new galaxies and solar systems. They blow dust and ice particles across the universe. They pull together under their own self-gravity and swirl to form stars and planets. The leftover ice and dust from these processes are where comets are born. SL9 was born under these circumstances. For billions of years, this comet hurtled through space at thousands of miles per hour. Each orbit, it got slightly closer to Jupiter's surface, until eventually Jupiter's gravity ripped it apart. At this point, it travelled as a string of pearls through space. One more orbit, and then collided into Jupiter's surface with the force of 300,000 atomic bombs.
We now know that comets are small bodies made up of frozen gas, dust, and rocks left over by the early formation of the solar system. Typically, comets orbit the Sun, but this is not the case as seen with SL9. SL9 broke up when it entered Jupiter's Roche limit. The Roche limit is the point at which the gravitational force of the body being orbited is greater than the self-gravity of the orbiting body. It is at this point SL9 broke up into a string of pearls.
We are now here at the top of Cabot Tower, where Brian is going to tell us about some of the more specific properties of SL9. The comet SL9 was 5 kilometres in width, and when it approached the Roche limit, it broke up into 21 fragments that ranged from hundreds of metres to 2 kilometres in width. These fragments then orbited for 2 years around Jupiter before crashing with the force of 300 million atomic bombs. The collision of SL9 into Jupiter was observed by astronomers all over the world using spacecraft and telescopes. The collision caused huge plumes which ranged from 2,000 to 3,000 kilometres in height. These plumes heated the atmosphere of Jupiter to 30 to 40,000 Celsius. This collision left dark ringed scars which were eventually erased by Jupiter's winds.
When SL9 crashed into Jupiter, it left behind some of its own chemical compounds, some of which, such as water, are still there today. This gave us an insight as to how the chemistry of Jupiter's atmosphere works. Scientists were excited by the data gathered from the event, as it provided insight into the structure and composition of comets. The fragments allowed for up-close assessment of cometary material and allowed us to learn about the dynamics of the solar system.
The collision of SL9 helped highlight the potential dangers of a cometary impact, and whilst the probability of an impact with Earth is relatively low, the consequences could be catastrophic. Now, the study of SL9 has helped scientists to understand the risks associated with such an impact and how to mitigate those risks if the worst was to happen.
As a group, we conducted an experiment using computer programs to test the relationship between bulk density and the Roche limit. The bulk density is how closely packed the comet is. A rock would have a high bulk density, whereas a sponge would have a low bulk density. Edward Roche derived a theoretical relationship between these two. He said that as the bulk density of the comet increases, the Roche limit should decrease. We reran the simulations with varying bulk densities of comets to test this relation and see if it agreed with our experimental findings.
So, using a computer program, we created a rubble pile for the comet, and we set the number of particles the pile was made of, the size of each one, and its mass. Then we gave some initial velocity and position to the pile as a whole and set it on its course to Jupiter. The program then iterated through each time step and saw how Jupiter's gravity affected the comet. It calculated its position through various points in time and stored all the data in files which we then used later. We then plotted our data on graphs, which allowed us to easily see the point at which the comet broke apart. We then found our own relationship between bulk density and disruption distance, and we compared it to the mathematical relationship from Edward Roche. Our relationship fitted the theoretical one pretty well. There were a number of areas though that our experiment could have improved on. We assumed that all the particles were the same size, and our time step, if it was smaller, would have given more accurate results.
So that concludes our talk. Thank you very much for listening. Together, we learned why comets tidally disrupt. We followed the life of the comet Shoemaker-Levy 9, from its creation in the early solar system to its fragmentation and final collision with Jupiter. And we explored the effect of the bulk density of a comet on its Roche limit. We hope you found the talk informative and, most importantly, interesting. And it just serves as a reminder of how incredible the universe is. Next time you look up at the night sky, just think what extreme, awesome events you might be witnessing among the stars.